Stroke Risk Prediction, Leveraging Predictive Analytics for Early Intervention by Chris Brown. Hi, and thank you all for joining. Today, I'm presenting my capstone project focused on predicting stroke risk using machine learning. Stroke is a leading global cause of death and long-term disability, and early detection is key to improving survival rates and reducing healthcare costs. In this project, I developed a predictive model that uses patient data such as age, glucose level, BMI, and medical history to estimate the risk of stroke. The goal is to assist clinicians in identifying high-risk individuals early so that preventative care can be administered before a stroke occurs. With this model, we aim to reduce late-stage diagnosis, improve outcomes, and lessen the financial strain on our healthcare system. The business problem is rooted in the inefficiency of current risk assessment models used in clinical settings. These models are largely rule-based and depend heavily on subjective interpretation by physicians, which introduces variability and limits predictive accuracy. The consequences of this are severe. Many strokes are only diagnosed after the fact, leading to avoidable suffering, hospitalization, and financial strain. By incorporating machine learning, we can standardize risk predictions and improve early detection. Our model helps identify key risk indicators and provides a more objective framework for intervention, which can have a profound impact on public health outcomes and healthcare expenditure. The project scope included data collection, cleaning, feature engineering, model selection, and deployment planning. Key goals included achieving high model accuracy while maintaining interpretability, creating a scalable solution for different hospital environments, and ensuring compliance with healthcare data standards. By using accessible datasets and machine learning methods, this project seeks to build a bridge between technical innovation and practical application in clinical workflows. The ultimate objective is to reduce the incidence and cost of strokes through smarter, data-informed decision-making in healthcare environments. The dataset used in this study came from Kaggl's stroke prediction dataset, comprising over 5,000 records and many key variables including age, gender, BMI, hypertension, smoking habits, and glucose levels. These features were selected because they align with well-established medical literature on stroke risk factors. For instance, age and hypertension are known to significantly elevate stroke risk. This dataset provided a good foundation for model training, and its size and structure made it ideal for supervised learning. Although it lacks real-time inputs, the diversity of variables offer a solid representation of risk factors typically assessed by clinicians. Data preprocessing involved cleaning, standardizing, and transforming the raw dataset to prepare it for machine learning. We filled in 201 missing BMI values using median imputation to preserve distribution integrity, treated outliers in glucose and BMI via renderization, and used smoke to balance the dataset due to the small proportion of stroke cases. These steps were essential for model stability, as imbalanced or messy data can produce misleading results, especially in healthcare where accuracy is critical. The result was a more robust dataset that could better support training and validation of reliable predictive models. Exploratory data analysis revealed critical trends. A bar chart of stroke prevalence across age groups showed a sharp rise in stroke incidence in patients over 60, consistent with clinical data. Correlation heat maps demonstrated strong links between hypertension, heart disease, and stroke. Furthermore, stratified analysis indicated that men who smoked were disproportionately affected. These analyses informed our model design and highlighted the real-world utility of predictive analytics in exposing hidden risk relationships that may not be immediately apparent during clinical assessments. Feature engineering improved the dataset's usability for machine learning. We grouped ages into ranges such as 0 to 40, 41 to 60, and 61 to 80 to better capture age-related trends. Categorical variables were encoded to convert them into numerical forms, essential for modeling training. For instance, we transformed marital status into binary values and applied one-hot encoding for multiple class features like work type and smoking status. This step was vital for helping models learn more efficiently and gave us finer control over model inputs, which ultimately improved prediction performance. We explored 4 models: logistic regression, decision tree, random forest, and XGBoost. Logistic regression was selected as a baseline due to its simplicity and ease of interpretation. Decision trees were evaluated for their transparency in decision making. Random forest and ensemble method improved accuracy and robustness by combining multiple decision trees. XGBoost, a gradient boosting technique, stood out for its ability to manage complex interactions and deliver high precision. Our focus was not only on accuracy, but also on ensuring that the model could generalize well and explain its predictions in a clinical setting. To ensure that our model generalized well to unseen data, we used an 80-20 train test split with stratified sampling to preserve class proportions. Smoke was applied to the training set, only to balance stroke and non-stroke cases. Evaluation metrics include AUC-ROC, precision, recall, and confusion matrix. XGBoost delivered the best performance with over 90% accuracy and a 0.93 AUC-ROC score. We also ran Monte Carlo simulations using 10,000 synthetic patient profiles to evaluate the model's reliability under varied input conditions, confirming that the model performed well across realistic clinical scenarios. Our deployment plan prioritizes clinical usability. The model will be deployed as a REST API and integrated into hospital electronic health record systems, allowing clinicians to view stroke risk scores in real time. A secure cloud environment will host the application, and dashboards will present predictions clearly. Deployment will begin in a single hospital unit as a pilot phase, followed by feedback collection, training, and a broader rollout. This phased approach ensures that the tool is adopted effectively, minimizing disruption and maximizing clinician trust and usability. The projected deployment costs of $35,000 include model development, hosting, licensing, training, and support. This investment is modest compared to similar tools such as Stanford's diabetes prediction model, which costs $50,000. We estimate cost savings of $100,000 annually through reduced stroke admissions and efficient triage. Early detection reduces the need for intensive care, long hospital stays, and rehabilitation. The model not only pays for itself within the first year, but continues to deliver return on investment in terms of both patient outcomes and operational efficiency. Our model contributes meaningfully to business goals by aligning predictive analytics with value-based healthcare strategies. It reduces emergency room congestion, allows for better use of clinical staff, and improves patient throughput. Most importantly, it empowers healthcare providers with data they can act on, leading to earlier interventions and fewer adverse outcomes. This project shows how data science can be applied to solve pressing problems in public health with measurable results. While promising, the model is not without its challenges. Healthcare environments are complex, and model adoption can be hindered by integration issues or skepticism among clinicians. One of the technical risks is data drift, where new patient data may no longer reflect the original training data. To address this, we recommend scheduling retraining of the model every 6 months. with monitoring for prediction accuracy and threshold performance. Training and model interpretability will also be key to building trust and ensuring continued clinical engagement. Going forward, I recommend adding more features to the dataset, such as cholesterol levels and family history of stroke, which could further improve accuracy. Incorporating SHAP values into the dashboard will enhance explainability and transparency, helping clinicians understand which variables drive risk predictions. In addition, exploring transfer learning methods could make the model more adaptable across hospital systems. The future of clinical decision support lies in explainable, adaptive AI models that can be tailored to local patient populations. In conclusion, this project demonstrates how machine learning can transform healthcare by enabling earlier stroke detection. The model achieved high accuracy and interpretability, and with proper deployment, it can directly improve clinical outcomes and reduce costs. This work serves as a blueprint for integrating analytics into preventive medicine. Thank you for your time and attention, and I welcome any questions or feedback you may have.